Every detail in this story comes from real scientific research and observation. Something is out there right now, moving toward the sun. It has been falling for longer than the dinosaurs existed. It carries ice that formed before the Earth had oceans. There is a place on its surface so cold that oxygen itself would freeze solid. And on one September morning in 2016, a spacecraft that had chased it for 12 years fell into it and never came back. What you are about to hear is the story of a comet, a piece of the solar system's beginning, and the machine that followed it farther than any human dared to go. The comet is called 67P. It is not smooth. It is not what anyone expected. It is two worlds pressed together, a shape no telescope had imagined, a silhouette that looks like something broken and slowly forgetting what it used to be. Its surface temperature drops to minus 230 degrees Celsius on the night side. Its gravity is so weak that if you stepped off a ledge, you would fall for 12 minutes before touching the ground again. And beneath that surface, beneath the dust and the ancient ice and the black organic crust, there is something that scientists still argue about in quiet rooms with coffee going cold on the table. There is water. There are amino acids. There is glycine, one of the simplest building blocks of protein, floating in the gas that bleeds off the surface when the comet gets close enough to the sun. This is not a story about something far away and irrelevant. This is a story about where you might have come from. Tonight, you will go there. You will stand on a surface 4.5 billion years old. You will watch two worlds press together in slow silence. You will feel the first warmth of the sun from 500 million kilometers away, and you will understand for a moment what it means for something dead to wake up. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. In the outer reaches of our solar system, far beyond Neptune and beyond the scattered disk of leftover rock and ice, there is a region that most people have never thought about. It is called the Oort cloud. It is not a cloud in any familiar sense, not a dense fog, not a visible mass of vapor. It is an enormous spherical shell of frozen objects, loosely bound by the sun's gravity, beginning roughly 2,000 astronomical units from the sun and extending perhaps 100,000 astronomical units outward, nearly halfway to the nearest star. Every comet that has ever passed through the inner solar system began its existence somewhere in that shell. 67P Churyumov Gerasimenko almost certainly did not start its journey there. It belongs to a class called Jupiter family comets, short-period comets whose orbits have been dragged inward and reshaped by gravitational interactions over millions of years. Its original home was likely the Kuiper belt, a flattened disk of frozen debris beginning just beyond Neptune at about 30 astronomical units from the sun. Sometime in the deep past, estimates suggest hundreds of millions to over 1 billion years ago, a gravitational encounter nudged it out of the Kuiper belt entirely, and it began to fall inward. You are there now. Not on the comet yet. You are somewhere in the space between worlds, watching. The sun from here is a very bright star, nothing more. It does not warm you. It does not illuminate anything more than faintly. The darkness here is a different kind of darkness than you have ever experienced. It is not the darkness of a room at night, not the darkness behind closed eyes. It is the darkness of genuine absence, the darkness of a place where photons are simply passing through, not arriving, not bouncing off anything, not collected by anything that sees. And there, in that darkness, is 67P. It is small. At this distance, in this light, it would be invisible to any instrument humanity has yet built. It is a rock, two rocks more precisely, composed of dust and ice in proportions that planetary scientists describe as a dirty snowball, or more accurately, a snowy dirt ball. The ratio of dust to ice in 67P leans toward dust. Roughly 75% of its composition by mass is porous, fragile, carbon-rich material, the kind of dark organic residue that coats many objects in the outer solar system. The remaining 25% is water ice, carbon dioxide ice, carbon monoxide ice, and smaller quantities of more complex frozen molecules. Its shape is unlike almost any other object scientists have closely observed. 67P has two distinct lobes. The larger lobe, which scientists on the Rosetta mission informally called the body, measures approximately 4.1 kilometers across its longest axis. The smaller lobe, called the head, is roughly 2.5 kilometers in diameter. They are connected by a narrow neck, a region of lower topography that the mission team named Hapi after the Egyptian god of the Nile inundation. This is not a shape that formed by erosion or by some gradual wearing down process. The leading hypothesis, supported by data gathered by the Rosetta mission, is that 67P is a contact binary. Two separate objects, formed independently in the early solar system, came together in the most gentle collision imaginable, closing at speeds of perhaps 1 meter per second or less, slower than a person walking, pressing their surfaces together over time until they became a single body. Two worlds that found each other across 4 billion years of cold space. You are watching them now, before that moment of contact, before the long history of the solar system had even fully formed. Understand what surrounds you. The early solar system was not the orderly, relatively stable system of today. 4.5 billion years ago, the region between the forming sun and the edge of the protoplanetary disk was a violent and densely populated place. Collisions happened constantly. Objects the size of mountains struck each other at kilometers per second. Planets grew by accumulating material, not gently but catastrophically. The inner planets were assembling under conditions of heat and pressure and continuous bombardment. But in the cold outer reaches, something different was happening. The temperatures beyond 4 astronomical units from the young sun, the so-called snow line, were low enough that water and other volatiles could condense into solid form. This is where comets were born. The same processes that were building the giant planets Jupiter, Saturn, Uranus, and Neptune were also scattering enormous numbers of smaller icy bodies outward, away from the planet-forming zone, into the cold, dark exterior of the solar system. 67Ps, two progenitor objects, the pieces that would one day become the body and the head, were among those scattered objects. They formed separately, perhaps in different parts of the same general region of the outer solar system, each accumulated from the same broad population of dust and ice and organic material, the primordial feedstock of the solar system. They were not unique objects. They were two of billions of similar bodies. What made them different from all the others is that they found each other. Imagine the vastness that had to be crossed. The outer solar system is not crowded. The distance between any two typical Kuiper Belt objects is enormous, far greater than the distance between the Sun and Mars. The probability of any two given objects actually meeting is vanishingly small. But the solar system is also ancient, and in 4.5 billion years, even low probability events occur. At some point in the outer solar system, these two icy bodies came into proximity. Their mutual gravity, weak because both are small, began to pull on each other. They did not collide violently. There was no explosion, no shatter, no crater-forming impact. The relative velocity between them was too low for that. They touched. They pressed. And very slowly, over what may have been thousands of years, they settled against each other. The material at the neck, the hoppy region, shows characteristics that are different from both lobes. It is smoother, fresher looking. Scientists interpret this as material that has been actively resurfaced, either by the gentleness of the original contact or by more recent geological processes. But that is much later. For now, you are simply watching two cold objects pressed together in darkness. The contact binary that would one day be called 67P is now a single body, awkward-shaped, irregular, spinning slowly on an axis tilted at roughly 52 degrees relative to its orbital plane. This obliquity is significant. It means that both poles of the comet experience extreme seasonal effects, long periods of intense illumination, followed by long periods of complete darkness as it moves around the sun. But for most of its history, 67P is not close to the sun. For most of its history, 67P is here. In the cold, in the silence. You are here too. Take a moment to understand the conditions around you right now. The temperature of the comet's surface in deep space, far from the sun, is driven almost entirely by the cosmic microwave background radiation, the faint thermal afterglow of the Big Bang, and by the extremely tenuous absorption of sunlight at this distance. The equilibrium temperature of an object at this remove works out to somewhere between -220 and -250 degrees Celsius, depending on the object's reflectivity and the exact distance from the sun. That is not far above absolute zero. Absolute zero, 0 Kelvin, -273.15 degrees Celsius, is the point at which all thermal motion of atoms and molecules ceases entirely. At -230 degrees, you are roughly 40 degrees above that limit. This means that even the most volatile ices on 67P's surface, carbon monoxide ice, carbon dioxide ice, the substances that will later be responsible for the most dramatic outgassing as the comet approaches the sun, are completely stable. Nothing is sublimating, nothing is escaping. The comet is sealed in cold, held still by temperatures that would make liquid nitrogen feel warm. The surface is black. Not the metaphorical black of space, but genuinely black. One of the darkest surfaces in the solar system, 67P, has an albedo of roughly 6%, meaning it reflects only 6% of the light that falls on it and absorbs 94%. This is darker than charcoal, darker than most rocks on Earth, comparable to the surface of a fresh asphalt road on a cloudy day. The darkness comes from its composition. The surface of 67P is coated in what planetary scientists call a refractory organic crust, a layer of complex carbon-based molecules that have been chemically processed over billions of years by cosmic radiation, ultraviolet light, and the slow chemistry of the cold. This is not a thin veneer. In places, the crust may extend meters below the visible surface before giving way to the cleaner ices beneath. Beneath that crust, protected from the radiation that would otherwise break it down, is water ice. And in that ice, distributed throughout the body of the comet in a way scientists are still characterizing, are organic molecules. Simple ones: methanol, formaldehyde, hydrogen cyanide, and more complex ones: glycine, phosphorus in forms relevant to DNA and RNA, ethylene glycol, which is a precursor to more complex organics. None of this is life, but some of it is the alphabet. You stand on this surface now, or rather you rest against it, because the gravity is so low that standing is almost meaningless. If your mass is 70 kilograms, the gravitational force pulling you toward the center of 67p is roughly equivalent to the weight of a single grain of rice on Earth. You are not standing on a surface. You are resting against one, the way a balloon rests against a ceiling. Beneath your hands, if you reach down and press them against the surface, the texture is more like compacted powder than solid rock. The surface layer of 67p is described by scientists as having the consistency of a very low-density aerogel, or perhaps a particularly fragile foam. The porosity of the material is estimated at between 70 and 80%. This means that roughly 3/4 of the volume of the comet is empty space, tiny vacuum pockets between loosely bonded grains of dust and ice. It is not solid. It is not loose. It is something in between, something that has never been given a precise name in human language, because nothing on Earth is quite like it. You press your hand against the surface, and it holds your weight, barely, but it holds. The texture beneath your fingertips is uniform and fine, like the surface of extremely dry compacted flour, but with no warmth, no elasticity, nothing that yields more than a few millimeters before becoming firm again. Around you, the comet stretches away in both directions. The curvature of the body is noticeable at distances of only a few hundred meters. It is a small world, and the horizon drops away quickly. The large lobe beneath you extends about 4 kilometers in its longest dimension, but from where you are, standing in one of the lower regions near the neck, you cannot see more than 1 kilometer or 2 in any direction before the surface curves below the horizon. Above you, and here the word above does not entirely make sense, because there is no meaningful up and down on a body with gravity this weak. The head of the comet rises like a cliff or a plateau. The neck region where you stand, the Hopi region, is illuminated more consistently than most of the surface because of the way the two lobes cast shadows and reflect light onto each other. But there is no meaningful light here. Not yet. In this period of the comet's long history, there is no illumination worth speaking of. The sun is a distant point. Its light takes hours to reach this far, and by the time it arrives, it carries almost no energy, a few tenths of a percent of what falls on Earth's surface. You sit in this darkness and you breathe, and then you remember that there is no atmosphere, and breathing is just habit, just the rhythm your body falls back on when it has nothing else to do. The silence around you is not the silence of a quiet room. It is the silence of an environment where no medium exists to carry sound. No air, no water, no material dense enough to transmit vibrations at any distance beyond direct physical contact. If you struck the surface beside you with your hand, and the motion would be so slow in this gravity that it would feel more like a pressing than a strike, you might feel a faint vibration through the surface, traveling through the compacted dust, but you would hear nothing. This is the comet's natural state. This is what it has been for most of its existence. This is where it lives. And it has been living here, or in regions not very different from this, for hundreds of millions of years. The solar system has been changing around it. Planets have migrated. Neptune moved outward, disrupting the outer solar system, scattering objects in all directions. Jupiter has continued its slow gravitational shaping of the inner system, pulling comets and asteroids into new paths, throwing some inward toward the sun and planets, flinging others into interstellar space. 67P has been touched by some of these changes. At some point, most likely in the last few 100 million years, though the exact timing is uncertain, the comet's orbit was deflected by a close encounter with Jupiter. This is how Jupiter family comets come to be. Jupiter is the dominant gravitational presence in the solar system after the Sun itself. Its mass, 318 times the mass of the Earth, gives it an enormous sphere of gravitational influence. Any object that passes through the inner solar system and comes close enough to Jupiter is subject to what orbital mechanics calls a gravitational perturbation, a change in trajectory caused by the gravitational pull of a passing body. For 67P, this perturbation was the most significant event in its history. Before the encounter, its orbit was large. Its farthest point from the Sun, the aphelion, was deep in the outer solar system, possibly in the scattered disk beyond Neptune. After the encounter, its orbit was dramatically reshaped. The aphelion was dragged inward. The orbital period, the time it takes to complete one full circuit around the Sun, dropped from something very long to something much shorter. Today, 67P orbits the Sun in approximately 6.45 years. Its closest approach to the Sun, its perihelion, brings it to about 1.24 astronomical units from the Sun, just slightly farther from the Sun than Earth is. Its farthest point, the aphelion, reaches only to about 5.7 astronomical units within the orbit of Jupiter. It is no longer a visitor from the outer cold. It is now a regular traveler in the inner solar system. And each time it passes close to the Sun, it loses part of itself. But that is not yet. Right now, in the long middle of its history, 67P is simply moving through space. Cold. Silent. Patient in the way that only very old things can be patient, not with intention, not with expectation, but with the simple mechanical persistence of an object following the laws of physics through time. The Sun is ahead, not close, not warm, but slowly across orbital timescales that dwarf any human concept of time. It is getting closer. And somewhere on a planet orbiting that Sun, in a period of history that has not yet arrived, the descendants of microorganisms that may themselves have arrived on comets will look up at the night sky and wonder what is out there. They will build instruments. They will build mathematics. They will calculate the trajectories of faint moving objects in the darkness. And one of those moving objects will be this one. This dark, cold, double-lobed piece of the solar system's beginning, carrying in its frozen interior the same organic molecules that, in one of science's most profound open questions, may have seeded the chemistry of life itself. For now, though, none of that has happened yet. The comet moves. The darkness holds. The cold does not change. And if you stay here long enough, if you remain perfectly still and let your attention simply rest on the surface beneath you and the stars above you, you begin to understand something about time that cannot be taught from a book. The universe does not care how long something takes. 4 billion years is not long to a rock. 4 billion years is simply the interval between one state and another. The comet was cold, and now, very slowly, it will become something else. You don't feel it yet, you won't for a long time, but something is changing. Somewhere far ahead, the sun is pulling. Not enough to notice. Not yet. But the vectors are shifting. The orbit is tightening. And in some future pass, in some orbit that has not yet occurred, something is going to happen on this surface that has never happened before. The ice beneath the crust is going to reach a temperature it has never reached. And it is going to move. But that is still to come. For now, you are here in the oldest quiet you will ever know. The surface beneath you is 4.5 billion years old. The stars above you are the same stars that have watched every moment of that time. And you are very, very small and very, very still, and the comet carries you forward through the dark at a speed you cannot feel, toward a sun whose warmth you cannot yet detect. Let your breathing slow. Let the cold settle around you, not as discomfort, but as distance. This is what the solar system feels like when nothing is disturbing it. This is the baseline. Everything else in this story is a departure from this silence. Keep it with you. You are going to need it. Because what comes next, the story of the machine that found this comet, the 10 years it took to reach it, the impossible landing on a surface no one had ever touched, that story begins on a different world entirely. It begins on Earth. And it begins with a question that planetary scientists had been asking for decades. What exactly is a comet made of? Not in the aggregate, not from a distance, not through spectroscopy alone, but up close. In contact. Touched? The European Space Agency asked that question formally in the 1990s. And the answer to that question became the Rosetta mission. But that comes next. For now, stay here. In the cold. In the dark. 4.5 billion years of silence, and you are moving through it, and the sun is still just a bright star, and everything is exactly as it has been for longer than life has existed on Earth. Rest in that. Just rest. The question was not a simple one. Scientists had been studying comets remotely for centuries, tracking their paths, analyzing the light that scattered through their tails, measuring the ratios of molecules in their outgassing. By the late 20th century, they had assembled a remarkably detailed picture of what comets probably contained: water ice, carbon dioxide, carbon monoxide, silicate minerals, complex organics. But probably was the operative word. Every comet that had been observed closely by spacecraft, by flyby missions, had been observed at speed and at distance. NASA's Giotto mission flew past Halley's Comet in 1986 at a relative velocity of 68 kilometers per second. It survived only a few seconds of close approach before being partially disabled by dust impacts. The images it returned were revolutionary, but they were snapshot images taken at enormous relative speed, with no ability to linger, no ability to study the surface over time, no ability to touch anything. Planetary scientists needed more. They needed to orbit a comet. They needed to land on one. They needed an instrument, a spacecraft, that could match velocities with a comet, fall into formation with it, travel alongside it for months or years, and ultimately place a lander on its surface. No one had ever done this. The physics of the problem are not trivial. Comets do not travel in nice circular orbits. They travel in highly elliptical paths, long stretched ovals that carry them from the cold outer solar system to the warm inner system and back again. Matching the trajectory of such an object from a launch pad on Earth requires a level of orbital mechanics planning that pushes the boundaries of what space agencies were capable of in the 1990s. The European Space Agency accepted the challenge. The mission was called Rosetta. Named after the Rosetta Stone, the ancient Egyptian artifact whose trilingual inscription unlocked the translation of hieroglyphics, opening an entire lost civilization to human understanding. The name was deliberate. The scientists who designed the mission believed that comets carried information from the earliest period of the solar system, information that was otherwise inaccessible, locked inside frozen bodies that had been preserved in the cold for billions of years. Rosetta was intended to be the key that unlocked that information. You are now leaving the comet behind temporarily. You are standing in Kourou, French Guiana, on the northeastern coast of South America. The date is March 2nd, 2004. The air here is humid, heavy with the equatorial heat that makes this location one of the most valuable launch sites on Earth. Kourou sits at approximately 5 degrees north latitude, which means that rockets launched from here benefit enormously from Earth's rotational velocity. The surface of Earth at the equator is moving eastward at roughly 465 meters per second relative to the planet's center. This free speed, available simply by launching eastward, reduces the fuel required to reach orbit. The Ariane 5 rocket standing on the launch pad tonight is one of the most reliable heavy-lift vehicles ever built. It has been prepared for months. Its payload, the Rosetta spacecraft, with the Philae lander attached, has been carefully mounted and integrated. Every subsystem has been tested to failure and back. Rosetta itself is a substantial piece of engineering. Its main body is a 3 meter by 2 meter by 2 meter aluminum structure, roughly the size of a large refrigerator truck's cargo section. Extending from either side are 2 solar panels, each 14 meters long, for a total wingspan of 32 meters. When fully deployed, Rosetta looks something like an enormous metallic manta ray, gliding through space with its panels outstretched. The solar panels are crucial, but they will not always be sufficient. At 67 P's distance from the Sun during its aphelion passage, around 5 astronomical units, the solar flux is only about 4% of what Earth receives. Rosetta's panels, even at their maximum extension, can only gather about 1 kilojoule of power at that distance. This is enough to operate in a minimal mode, but not enough to power the full science payload. This constraint shaped everything about the mission. Rosetta carries 11 scientific instruments directly on its body, These include OSIRIS, an optical imaging system capable of resolving features on the comet's surface to a scale of centimeters from close orbit; Rosetta, a mass spectrometer designed to analyze the chemical composition of the gas and dust surrounding the comet; MIRO, a microwave radiometer for measuring subsurface temperatures; VIRTIS, a combined visible and infrared mapping spectrometer; and 7 others: magnetometers, particle analyzers, plasma wave instruments, each designed to characterize a different aspect of the comet environment. The Philae lander, named after the island in the Nile where an obelisk was found that helped Champollion decode Egyptian hieroglyphics, is attached to the side of Rosetta. It weighs approximately 100 kilograms on Earth, though its weight on 67P will be negligible. It carries 9 instruments of its own, including a drill, the SD2 sample drill, designed to extract material from up to 23 centimeters below the surface and deliver it to onboard analyzers. It also carries 3 landing systems for a surface with gravity too weak to simply set down on safely: an ice anchor, a screw designed to drill into the surface and lock the lander in place; cold gas thrusters on the top of the lander, designed to push it downward toward the surface to counteract any bouncing; and harpoons, 2 of them, designed to fire into the surface and anchor the lander on contact. All 3 of these systems will, in the end, fail to function as designed. But that too comes later. The countdown reaches 0. The Ariane 5 ignites. You are watching from a safe distance. The launch perimeter here is measured in kilometers, because the explosive energy of a fully fueled heavy-lift vehicle is not a thing to stand near. The sound reaches you about 3 seconds after the visual, a rolling physical pressure of sound that you feel in your chest before your ears fully register it as noise. The rocket climbs, slowly at first, then with accelerating speed. The exhaust plume expands as it rises through the lower, denser atmosphere, spreading outward into a white cone below the ascending vehicle. At this time of the morning, the exhaust glows orange-yellow at the base where combustion is most intense, and becomes bright white higher up where the gases cool and expand. Within 2 minutes, the solid rocket boosters separate. Within 4 minutes, the main stage cuts off and the upper stage takes over. Within 26 minutes from launch, Rosetta is in a parking orbit around Earth. It is not yet going to 67P. It is in fact not yet going anywhere near 67P. The trajectory required to reach a Jupiter family comet, a body whose orbit extends to beyond 5 astronomical units from the Sun, cannot be achieved in a single launch. The energy required to escape the inner solar system and match velocities with an object in the outer solar system is more than any rocket currently in existence can provide directly. The solution is gravity assists, also called gravitational slingshots or swing-bys. Gravity assists use the gravitational field of a planet to change a spacecraft's speed and direction without burning fuel. The spacecraft approaches a planet on a carefully calculated trajectory, passes close by, and leaves on a different trajectory, having transferred a tiny amount of the planet's orbital momentum to itself. The planet's orbit is affected too, of course. Conservation of momentum applies equally to both objects, but because a planet is so enormously more massive than any spacecraft, the effect on the planet is completely immeasurable. Rosetta required 4 gravity assists to reach 67P, 3 around Earth, 1 around Mars. The first Earth gravity assist came in March of 2005, exactly 1 year after launch. Rosetta had spent that year in an orbit around the Sun that brought it back close to Earth, allowing it to use Earth's gravity to pick up speed and redirect toward Mars. The Mars flyby occurred in February 2007. Approaching Mars at a relative velocity of several kilometers per second, Rosetta swept within just 250 kilometers of the Martian surface, closer than most Mars-orbiting spacecraft operate. At this distance, the planet fills a significant portion of the visual field. You are on Rosetta now. You do not see much. There are no windows on the spacecraft, but the OSIRIS camera system is active, and if you could see what it sees, you would see Mars as a reddish-brown disk, detailed enough to make out the darker volcanic highland regions from the lighter dust-covered plains. You are passing at a speed relative to Mars of several kilometers per second. And in this brief pass, the gravity of Mars does something precise and beautiful to your trajectory. It bends it. The curve of Rosetta's path changes, subtly but measurably, as Mars's gravitational field pulls on the spacecraft during the closest approach, and then releases it on the other side. The net effect is a change in velocity. Rosetta leaves the encounter on a different heading and at a different speed than it arrived. Not fast enough yet. 2 more Earth gravity assists followed, in November 2007 and again in November 2009. Each time Earth's gravity bent Rosetta's path a little further outward. Each time the spacecraft's aphelion, the farthest point of its orbit from the Sun, extended a little further into the outer solar system. Each time the trajectory grew closer to an intercept with 67p. Between these gravity assists, Rosetta was also doing science. It flew past the asteroid Steins in September 2008, passing within 800 kilometers and returning the first close images of this small S-type asteroid. It flew past the asteroid Lutetia in July 2010, a much larger irregular body, and returned images of a battered ancient surface covered in craters and geological complexity that surprised scientists. These were not the mission's primary objectives. They were opportunity science, scientific returns from targets of opportunity that happened to lie along a trajectory optimized for other purposes. Rosetta is good at this. It was built to last. In June 2011, that durability was tested in a specific way. The spacecraft was approaching its aphelion, its farthest point from the Sun, at approximately 5.3 astronomical units. At this distance, solar power was reduced to the point where Rosetta could not sustain operations of its science instruments or even its full attitude control systems. The mission team made a decision. They put Rosetta to sleep. On June 8, 2011, all non-essential systems aboard Rosetta were powered down. The spacecraft's internal clock was set to wake the system up at a specific time in the future. The last communication link was maintained just long enough to confirm the shutdown was proceeding correctly, and then silence. For 31 months, Rosetta drifted. It received no commands from Earth. It sent no data. Its instruments were off. Its transmitters were off. Its attitude control thrusters fired only occasionally, using the minimum amount of fuel necessary to keep the solar panels pointed roughly toward the Sun. The mission team could not communicate with it. They could not tell whether it was functioning correctly. They could not know for certain that the onboard clock, the one thing standing between the mission's success and its permanent failure, was ticking correctly. They waited. This is worth sitting with for a moment. The Rosetta spacecraft was the result of 20 years of development, billions of euros of investment, and the coordinated work of hundreds of engineers and scientists across multiple countries. It had taken 10 years to reach this point, and now it was silent, drifting in the outer solar system, completely beyond the reach of any human intervention. If the clock failed, if the wake-up command never fired, the spacecraft would drift past its intended wake-up point, past its intended intercept with 67P, and eventually into an orbit from which it could never complete its mission. There was nothing the mission team could do except wait and trust the engineering. On January 20th, 2014, at 18 hours, the onboard clock triggered Rosetta's wake-up sequence. The sequence began with the spacecraft's star trackers, the devices used to determine orientation, warming up and beginning to fix the spacecraft's attitude. Then the thrusters fired, stabilizing the spin. Then, one by one, the systems came online. Rosetta began composing a signal. The signal traveled from the spacecraft to Earth at the speed of light. At the distance Rosetta was from Earth at that moment, approximately 807 million kilometers, the signal took approximately 45 minutes to arrive. Mission controllers at the European Space Operations Center in Darmstadt, Germany, were waiting. The room was crowded. The scheduled wake-up time had been announced publicly, and scientists from across the mission had gathered to watch. At approximately 18 hours 45 minutes, the signal arrived. Rosetta was awake. You feel something here, not sentiment exactly, but the recognition of what 31 months of silence, followed by 45 minutes of waiting, and then a single signal actually means to the people who built this machine, to the people who had spent their careers working toward this mission, who had calculated the trajectory years in advance, who had built the instruments and the lander and the fuel tanks and the wake-up clock, who had trusted all of that engineering to do its job while they waited in rooms on Earth, watching clocks. The signal that arrived in Darmstadt contained telemetry, the health and status data from Rosetta's systems. The solar panels were oriented correctly, the attitude was stable, the instruments were beginning their warm-up sequences, the fuel reserves were within the expected range. Everything was working. Over the following weeks and months, the mission team used Rosetta's thrusters to refine its trajectory, the long approach path that would bring it into proximity with 67P. But first, they needed to see it. In February 2014, Rosetta's OSIRIS camera first detected 67P. It appeared as a point of light, indistinguishable at this distance from any other faint moving object in the field of view. The images were combined and processed, and the motion of 67P against the background of fixed stars was measured. Over the following months, as Rosetta closed the distance, the comet grew in the images. In late May, the first shapes began to emerge. Something was wrong. Or rather, something was unexpected. The pre-mission models of 67P's shape, based on light curve analysis from ground-based observations, had predicted an elongated but relatively simple body, rotating light curves. The variation in brightness as a rotating object presents different cross-sections to an observer, suggested an object perhaps a third longer in one axis than the others, but nothing more complex than that. What OSIRIS revealed in June 2014 was something completely different. The comet had a neck. It had 2 lobes. It looked to the scientists who first processed these images like a rubber duck, like 2 spheres stuck together, like a contact binary, which is exactly what the data would eventually confirm it to be. The mission team stared at these images and understood almost immediately that the landing scenario they had planned for years was no longer valid. Landing on a smoothly rotating, roughly oblate body is a challenging but tractable problem. Landing on a double-lobed object with irregular topography, extreme slopes between the lobes, rapidly varying illumination conditions, and a neck region that was unlike either of the 2 lobes individually, this was a different problem entirely. The engineers and scientists began immediately to revise everything. Rosetta was now close enough that its camera could resolve features on the surface. And the surface was nothing like anything they had planned for. 67P's surface is not uniform. It is covered in regions of dramatically different character: smooth, sediment-covered plains, rough, fractured cliff faces, depressions that look like collapsed pits, towering cliffs of consolidated material, regions where the bedrock structure of the comet is exposed, showing a layered internal architecture, the layers not from sedimentary deposition as they would be on Earth, but from the way volatile rich layers had been deposited and preserved during the comet's formation billions of years ago. One region near the neck, the Hopi region, where you were standing during part 1, is particularly smooth, covered in a fine-grained material that forms ripples and dunes. Scientists studying these features determine that the ripples are not formed by wind. There is no wind on a comet, but by the outgassing of volatiles from the surface, which can carry dust particles short distances before they settle back under the weak gravity. The comet was already active. Even at this distance, still more than 3 astronomical units from the Sun, outgassing was occurring. Not dramatically, not enough to produce the spectacular tail that comets display near perihelion, but enough to be measured, enough to be observed as a faint coma, a thin atmosphere of gas and dust extending thousands of kilometers from the nucleus. Rosetta flew through this coma as it approached. The instruments began to detect molecules: water vapor, carbon dioxide, carbon monoxide, methane, ammonia, hydrogen sulfide, hydrogen cyanide, formaldehyde. The outgassing rate at this point was modest. Estimates put it at around 1 kilogram of water vapor per second, rising as the comet's sunward side warmed. Rosetta arrived at 67P in August 2014. Arrived is perhaps not quite the right word for what spacecraft do when they rendezvous with small bodies. Rosetta performed a series of deceleration burns, firing its thrusters against its direction of travel to reduce its velocity relative to 67P. The final approach speed was reduced to a walking pace, and then to something slower than a walking pace, until Rosetta was effectively keeping formation with the comet, separated from the nucleus by distances of between 30 and 100 kilometers. You are back on the spacecraft now. You are looking at 67P from a distance of approximately 50 kilometers. This is what you see. A dark, irregular shape against the blackness of space, its outline sharp and clear, its surface detailed enough at this distance that individual large features are visible. The two lobes, the neck between them, the cliff at the large lobe's southern edge, a sheer drop of hundreds of meters, the smooth plains of Hapi, the rough, chaotic terrain on the body's opposite side, covered in consolidated material and deep fractures. The comet rotates once every 12.4 hours. As it rotates, different parts of the surface come into sunlight and return to shadow. You watch features emerge from darkness on one side, traverse the sunlit portion of the nucleus, and disappear again on the other side. The Sun at this distance is roughly 4 times farther from 67P than the Sun is from Earth. But the nucleus is so dark, its albedo so low, that the sunlit surface absorbs that reduced solar energy efficiently and begins to warm. Beneath the black organic crust, the water ice is warming. Slowly, degree by degree. The KO2 ice, which has a lower sublimation temperature than water ice, is already responding. Thin streams of gas, carrying dust with them, rise from the surface in columns, too faint to see directly from this distance, but visible in the instrument data. The comet is beginning to wake. Rosetta watches, it maps, it measures, it records. And the mission team on Earth, studying the data as it arrives after its 45 to 50-minute transmission delay, begins the most difficult task the mission has set for them. They need to find a landing site. For Philae, there are constraints that quickly narrow the options. The site must be illuminated for enough hours per rotation to keep Philae's solar panels producing power during its science operations, but not so illuminated that the surface temperature rises high enough to threaten the lander's systems. The site must have terrain that Philae's landing legs can accommodate, too steep and the lander tips over, too rough and it cannot stabilize. The site must be accessible from Rosetta's orbital position. The trajectory of Philae's release must result in a flight path that reaches the surface at the correct angle and speed. And the site must be scientifically interesting. There is no value in landing somewhere geologically uniform. 5 candidate sites were selected by late August 2014. They were named with letters: Site A, Site B, Site C, Site I, Site J. After weeks of analysis, Site J was selected as the primary landing site. Site J, later named Agilkia, after the island in the Nile to which the temples of Philae were relocated when the original island was flooded by the construction of the Aswan High Dam, is located on the smaller lobe of 67P, the head. It is relatively smooth by the standards of 67P's surface, which means it is covered in fine-grained sediment rather than exposed consolidated material. It has illumination of roughly 6 to 7 hours per rotation at the time of landing. It has slopes mostly below 30 degrees, which the lander's systems are designed to handle. It is not perfectly safe. No site on 67P is perfectly safe, but it is the best option available. The date for the landing is set: November 12th, 2014. Rosetta positions itself. The mission team on Earth runs simulations. The night before the landing, Philae's systems are powered on and checked. The lander, which has been in a low-power hibernation state since before the 31-month sleep period, wakes up slowly. Each system checks in. The instruments are alive. The landing gear is ready. The harpoons are or appear to be ready. The cold gas thruster on the top of the lander is or appears to be ready. On November 12, 2014, at 8 hours 35 minutes Universal Time, Rosetta releases Philae. The separation is gentle. A small spring-loaded mechanism pushes the lander away from the spacecraft at a relative velocity of about 18 centimeters per second, roughly the speed of a very slow walking pace. Philae begins to fall. Not fall in the conventional sense, not the rapid, accelerating drop that the word suggests. The gravity pulling Philae towards 67P's surface at this point, some 22 kilometers above the landing site, is approximately 1/10,000th of Earth's surface gravity. The acceleration is roughly 1 millimeter per second per second. At that rate of acceleration, falling 22 kilometers takes hours. Specifically, 7 hours. 7 hours of slow, silent descent. You are Philae now. You are falling. The comet below you slowly resolves into more detail with every passing hour. The smooth plains of Agilkia grow in your field of view. The sun is low on the horizon. The illumination at the landing site is adequate but not bright. Rosetta is above you, watching. Its cameras track your descent. Its instruments monitor the environment around you. It is the closest thing to a safety net available, though there is nothing at this point that Rosetta can actually do if something goes wrong. 7 hours. This is what it takes to fall from where you are to where you are going. In that time, think about what this means. The mission was launched in March 2004. It reached the comet in August 2014. 10 years and 5 months of travel, 4 gravity assists, a 31-month hibernation, months of orbital mapping, and weeks of landing site analysis, all of it building toward this 7-hour fall. The mission team on Earth is not watching in real time. The signal delay is approximately 28 minutes at this point. 28 minutes for a command to reach Rosetta, 28 minutes for a response to return. Any event that occurs on the surface of 67P will be known on Earth almost half an hour after it happens. There is nothing anyone can do in real time. There is nothing left to do but fall. Hour 6. The surface of Agilkia fills your field of view now. You can see individual boulders, a meter or more in diameter, scattered across the smooth sediment. You can see the texture of the surface, the fine-grained material, the slight undulations, the shadows cast by small topographic features. You are descending at approximately 1 meter per second. Your landing gear, 3 legs arranged at 120-degree intervals, is deployed. Your harpoons are charged. Your cold gas thruster is ready. The surface rises toward you. Hour 7. You touch. The landing legs contact the surface of 67P at 16 hours 3 minutes Universal Time on November 12th, 2014. At this moment, the harpoons are supposed to fire. They do not fire. The thruster on top of the lander is supposed to push Philae downward into the surface. It does not work. The ice screws in the landing legs are supposed to drill into the surface. They spin but find no purchase. The surface beneath them is too hard, more consolidated than the smooth sediment visible in the images had suggested. Without the harpoons, without the thruster, without the screws, Philae bounces. The rebound velocity from the soft contact with the surface is tiny, perhaps 3 centimeters per second, but on a body with gravity 1/10,000th of Earth's, 3 centimeters per second is more than enough to send a lander airborne again. Philae rises back into the sky of 67P. It rises nearly 1 kilometer above the surface. It moves laterally across the face of the comet, and it falls again. The second impact is at 17 hours 25 minutes. It bounces again, a smaller bounce this time, a few meters, and then comes to rest in a new location. This location is not a Gilkia. The comet has carried Philae somewhere else. The exact final resting place of the lander is not immediately known. The telemetry data shows that Philae is stable, upright, with its instruments functional, its solar panels receiving some light. But how much light? Not enough. The final resting location, later named Abydos, after the ancient Egyptian city, is in the shadow of a cliff face on the large lobe of 67P. The solar panels receive illumination for only about 1.5 hours per 12-hour rotation. Philae's battery, fully charged before landing, will last approximately 64 hours. 64 hours to do the science of a mission that took 10 years to reach this point. The instruments begin to work immediately. The MUPUS thermal sensor, a probe designed to be hammered into the surface, is deployed. It hammers. The surface resists at a level far beyond what the engineers expected. The hammer reaches maximum force and stops before penetrating more than a few centimeters. The surface beneath Philae is not soft sediment. It is hard, harder than expected, closer to hard ice than loose powder. This is itself a discovery. The concert radio sounding instrument begins broadcasting, sending radio waves through the nucleus of the comet, with Rosetta receiving them on the other side. The delay and distortion of these signals as they pass through the comet's interior gives scientists the first measurements of the comet's internal structure. The interior is remarkably homogeneous. It is not layered in the sense of having dense rock in the center and ice outside. It appears to be more or less the same throughout, porous, loosely consolidated, with a high void fraction. ORLIS, the descent imaging system, captured images throughout the descent and at touchdown. CEVA, the surface imaging system, captured panoramic images from the surface. PITO-ILMI and COSAC, the chemical analysis instruments, sniffed the air around the lander and analyzed the composition of the gases. In those 64 hours, Philae transmitted more than 470 megabytes of data. In those 64 hours, it returned the first surface measurements ever taken from a cometary nucleus. And then the battery ran out. The instruments shut down. The transmitters went silent. Philae was not dead. Its solar panels continued to trickle charge a capacitor bank, but it had nothing like the power needed to operate its systems. It was in the dark on the surface of a comet, under a cliff, 400 million kilometers from Earth. Rosetta continued to orbit, continued to map, continued to measure. The comet continued its fall toward the sun. And you, here in this moment, feel what it means to have reached this far, to have crossed 10 years of space, and come to rest in the shadow of a cliff on a frozen ancient world, carrying instruments that had found exactly what the scientists hoped for and more, and then to fall quiet, waiting for the sun to rise enough to charge the panels again, waiting in the dark of Abydos while the comet moved through space, carrying everything forward together. The comet, the lander, the instruments. All of it moving toward the sun. All of it waiting for warmth. That warmth is coming. And when it arrives, it will change everything about this surface that has been cold and still for 4.5 billion years. The comet is not done. Neither is this story. Rest now. The journey continues. Abydos is quiet. The lander rests against a surface it was never supposed to reach, wedged in shadow, tilted at an angle that prevents 2 of its 3 solar panels from receiving any useful light. The third panel catches about 90 minutes of illumination per rotation. It is not enough to operate the instruments. It is not enough to transmit. It is barely enough to maintain the minimum charge needed to keep the clock running. Philae is not dead. It is waiting. It does not know it is waiting. It is a machine, and machines do not know things in that sense, but its capacitors accumulate charge slowly, and its onboard computer checks its power state on a regular cycle, and on each check the answer is the same: not enough, not yet. Meanwhile, the comet moves. This is the part of the story that is easy to lose track of. The simple, continuous, unstoppable physics of an object in an elliptical orbit, closing the distance to the sun by kilometers every second, inexorably without pause. 67P is moving at approximately 19 kilometers per second in its orbit. That is faster than any bullet ever fired by a human weapon, and it is a slow speed by the standards of the inner solar system. Every second, 19 kilometers of space between 67P and the sun disappear. Every hour, 68,000 kilometers. Every day, 1.6 million kilometers. Rosetta orbits above, mapping the surface with its OSIRIS camera system, analyzing the thin outgassing coma with its spectrometers, monitoring the slow but measurable increase in the comet's activity as it warms. And it is warming. Not quickly, not dramatically, not yet. In October 2014, before the landing, while Rosetta was still characterizing the nucleus from a safe distance, the outgassing rate of water vapor from 67P was measured at approximately 300 grams per second. That is roughly the volume of a moderately large water bottle evaporating from the comet's surface every single second. By January 2015, the rate had increased to approximately 1 kilogram per second. By April, 3 kilograms per second. By August, when the comet reaches its closest point to the sun, the rate will be measured in tons per hour. But that progression, that steady, accelerating loss of the comet's substance, is still ahead. For now, in November and December 2014, the changes are subtle enough to measure only with sensitive instruments. The coma is thickening. The dust component, fine particles lifted from the surface by the expanding gas, is increasing in density around the nucleus. Rosetta has to adjust its orbit as conditions change. In the early months of the mission, Rosetta operated in triangular orbits, not circular, because the comet's weak and irregular gravity makes circular orbits unstable, but rather in deliberate sequences of hyperbolic arcs around the nucleus. The spacecraft would approach, arc around, recede, and approach again from a different angle. As the comet becomes more active, this becomes more complex. Gas and dust streaming away from the nucleus exert small but measurable pressure on Rosetta's solar panels and body. This pressure, radiation pressure from sunlight reflected off the dust, and direct momentum transfer from gas molecules striking the panels perturbs the spacecraft's trajectory in ways that must be continuously corrected. The mission team on Earth watches these perturbations. They are, in fact, measuring the comet's activity by watching how hard the environment is pushing on their spacecraft. You are Rosetta now. You are in orbit above a world that is slowly coming alive. Below you, the surface of 67P rotates through the 12.4-hour cycle of a cometary day. The happy region, the smooth neck between the two lobes, is particularly active. As the comet rotates, the morning terminator, the line between the night side and the day side, sweeps across the happy plains, and at the moment of first sunlight, something happens. The transition from cold shadow to sunlight causes a rapid local temperature change on the surface. The uppermost millimeters of the surface warm first. Beneath them, barely insulated by the thin organic crust, volatile ices begin to respond. Carbon dioxide ice, which sublimes at roughly -78 degrees Celsius, begins to transition from solid to gas at temperatures that the sunlit surface easily reaches. The gas has nowhere to go but outward. It expands through the porous surface material, carrying dust grains with it, and exits into space as a thin jet, a stream of gas and dust, invisible to the naked eye but detectable by Rosetta's instruments and visible in long exposure camera images as a faint plume above the surface. These jets are not random. They emerge from specific locations, driven by the local topography and composition of the surface. The Happy region produces consistent jets from consistent source locations. The jet activity is highest in the first few hours after local sunrise and diminishes as the surface temperature equilibrates and the locally available volatiles are temporarily depleted. Then the surface rotates back into shadow. It cools. The volatiles in the near-surface layer, barely depleted, because the gas that escaped came from only the uppermost fraction of a millimeter, restabilize, and the cycle repeats. This process, sublimation-driven jet activity triggered by the terminator crossing, is one of the primary mechanisms by which comets lose mass. Over a single orbit of 67P around the Sun, 6.45 years, the comet loses somewhere between 200 million and 800 million kilograms of material. That sounds enormous until you consider that the total mass of 67P is approximately 10 trillion kilograms, 10 to the 13th power. At current loss rates, 67P could sustain this level of activity for roughly 10,000 more years before being completely depleted. But the loss rate is not constant. Each approach to the Sun is slightly more depleting than the last, because the internal reservoir of volatiles accessible to the surface sublimation process diminishes over time. 67P has been a Jupiter family comet, making regular close approaches to the Sun for at least a few 100,000 years. It has already lost a significant fraction of its original volatile inventory. It is older than it looks, in the relevant sense, the sense of how much of its original material it still retains. It is considerably depleted compared to a fresh comet arriving from the Oort cloud for the first time. But it still has enough to wake, enough to change, enough to do what it is about to do. In March 2015, something unexpected happened on the surface of 67P. Rosetta's OSIRIS camera, during a routine imaging sequence, captured a sudden brightening of the surface in a region on the large lobe called Imhotep. The brightening lasted for approximately 12 days. Over those 12 days, the surface of Imhotep changed in visible, measurable ways. A large circular depression that had existed since Rosetta first began imaging the comet, a smooth-floored pit roughly 800 meters in diameter, had changed its character. Its smooth floor, previously covered in fine-grained material, had developed new features. Bright patches of freshly exposed material appeared. The albedo of those patches was dramatically higher than the surrounding dark terrain. The bright material was water ice. Not the processed, radiation-darkened ice of the surface crust, but relatively fresh ice, newly exposed by some process that had removed the overlying material. The leading explanation for what happened in Imhotep in March 2015 involves a collapse. The subsurface of 67P is not structurally solid. Its high porosity, the roughly 70 to 80% void fraction discussed earlier, means that there are effectively hollow spaces and weakly consolidated regions throughout the nucleus. When sublimation occurs in the near-surface layers, the gas that escapes must navigate through this porous structure. Under the right conditions, when the sublimation rate is high enough and the surface material above a void space is thin enough, the surface can collapse. Not violently. Slowly, the surface material drops into the space below, exposing deeper material to sunlight for the first time in perhaps millions of years. Deeper material that still contains relatively pristine ice. Material that had been protected from radiation and thermal processing by the overlying layers above it. This is one of the most scientifically significant observations made during the entire Rosetta mission, not because a collapse event is surprising in itself, but because the bright water ice exposed by that collapse is spectroscopic evidence of what lies beneath the processed exterior of the comet, beneath the dark crust, beneath the organic residue. There is still clean ice. There is still the original material of the early solar system, preserved in the interior of this body, surviving 4.5 billion years of cosmic irradiation because it was buried just deeply enough that the radiation never reached it. You are watching from above. The comet below you is a world in the process of being unmade. Not quickly, not catastrophically, but steadily, orbit by orbit, pass by pass, shedding material into the space around it. Water vapor, carbon dioxide, organic molecules, dust, spreading itself thinly into the inner solar system, leaving trace amounts of itself on every surface it passes near, contributing a tiny fraction of its substance to the environment of the planets. Some of that material will be swept up by the solar wind and pushed outward. Some will drift in low-density clouds along the comet's orbital path, where Earth crosses it twice a year, and the particles burn up in the upper atmosphere as meteor showers. Some will fall on Earth directly, too small to cause any visible event, just microscopic grains drifting through the stratosphere, settling eventually onto the surfaces of glaciers and ocean floors and rooftops and the backs of your hands. The comet is distributed. It does not stay in one place. It gives itself to the solar system, a little at a time in every orbit. On June 13th, 2015, something happened that the mission team had been waiting and hoping for since November of the previous year. Rosetta's communication systems detected a signal. A weak signal, intermittent and unstable, but unmistakable in its origin. It was coming from the surface of 67P. Philae was awake. The comet had carried the lander close enough to the sun that the solar panels, even the two that were partially shadowed, were generating enough current to charge the capacitor bank to an operational level. The charge threshold crossed, the onboard computer initialized. Philae transmitted. The signal contained stored telemetry from the months of hibernation, temperature data, power state data, the internal record of a machine that had been sitting in the dark on the surface of a comet for 7 months, waiting. Over the following weeks, Rosetta and Philae exchanged communications on 8 separate occasions. The lander was functional. Its instruments were operational. It was transmitting stored data and responding to commands. But the communications were never stable enough or sustained enough to conduct the full science program that had been planned for the surface mission. The geometry was the problem. Philae's exact position, tucked against a cliff face in the shadowed region of Abydos, meant that Rosetta could only receive Philae's transmissions when its orbital position placed it in the narrow cone of directions from which the lander's antenna could reach it. And the comet's increasing activity was making close orbital operations more dangerous. As 67P approached perihelion, Rosetta was forced to back away from the nucleus to protect itself from the increasingly dense outgassing environment. At greater distances, Philae's signals became even harder to receive reliably. The last confirmed communication with Philae was received on July 9th, 2015. After that, silence. Rosetta's team continued to listen. They continued to transmit commands toward the surface. Nothing came back. What happened to Philae after July 9th is not entirely certain. The most likely explanation is that the comet's increasing outgassing activity, which was, by this point, lifting material from the surface and redistributing it, may have shifted the material around the lander, possibly altering the angle at which its panels received light, possibly burying it further under relocated surface material. Or the power simply never reached the threshold again. Or the hardware, which had experienced temperature swings from -180 degrees Celsius during the long cold hibernation to warmer conditions as the comet neared the sun, had degraded beyond the point of reliable function. The machine had done what it could. What it had managed to do in those 64 initial hours and those 8 brief subsequent contacts was substantial. SOSAC, the cometary sampling and composition experiment, had detected 16 organic compounds in the gas immediately above the landing site. 16, including 4 that had never been detected in a cometary environment before, including glycolaldehyde, which is a simple sugar. The presence of organic molecules on the surface and in the outgassing of 67P was not by itself surprising. Scientists had expected organics. What was surprising was the complexity, the variety, the specific molecules present and in what ratios gave researchers new data for modeling what the chemistry of the early solar system's building blocks actually looked like. And it gave new weight to a question that was already being asked seriously in astrobiology departments around the world. Did comets help start life on Earth? Not as a simple yes or no. The question is more subtle than that. The hypothesis, sometimes called panspermia in one of its variants, though that word carries connotations the researchers prefer to avoid, is that comets may have delivered significant quantities of organic material to the early Earth. The timeline is relevant here. The Late Heavy Bombardment, a period approximately 3.8 to 4 billion years ago, during which the inner solar system experienced an unusually high rate of impacts from comets and asteroids, coincides, roughly, with the earliest evidence for life on Earth. The earliest confirmed microbial fossils are approximately 3.5 billion years old. The earliest geochemical signatures potentially indicating biological activity are approximately 3.8 billion years old. This is not proof of anything, correlation is not causation, and the timing could be coincidental. Life may have begun on Earth independently, using chemistry that was entirely terrestrial. But the data from Rosetta's instruments adds new specificity to the question. The organic molecules detected in 67P's outgassing are not exotic or alien. They are the same molecules that are found in meteorites, in interstellar clouds, in the hydrothermal vents at the bottom of Earth's oceans, where some scientists believe life may have begun. They are a common chemical vocabulary. And comets, crossing the inner solar system, losing material with every orbit, distributing that material across the paths of planets, are one of the most efficient delivery mechanisms the solar system has ever possessed. You do not need to resolve the debate tonight. The scientists have not resolved it either. But you are here, orbiting a body that contains the same organic alphabet as the first cells that ever metabolized energy on Earth. And the coincidence, if it is a coincidence, is worth sitting with. The surface below you is losing itself to the sun. Slowly. The jets are visible now on the imaging data, not just one or two, but dozens of identified source locations across the nucleus, each one a plume of gas and dust, rising from the surface and expanding into the coma. The coma itself has grown. By June 2015, the hydrogen coma, the outermost, most diffused envelope of hydrogen atoms produced by the photodissociation of water vapor, extends more than 120,000 kilometers from the nucleus. The dust tail, the stream of particles pushed back by solar radiation pressure, now stretches for tens of thousands of kilometers behind the comet, in the direction away from the sun. The ion tail, the more structured, straighter tail formed by ionized gas molecules being swept back by the solar wind, extends even farther. 67P is at this point visually spectacular. Not to the naked eye, it is still too faint for that, too small, too far from Earth's position in its own orbit for easy naked eye viewing. But to a telescope, to a camera with a long enough exposure, 67P in June and July of 2015 is a comet. Not just a cometary nucleus, not just a dark, irregular rock in space. A comet with a coma and a tail, expressing all the visual drama that the word comet has conjured in human imaginations since the first person looked up and noticed a fuzzy star with a streak of light behind it and wondered what it meant. You are inside that drama now. You are in the coma. The gas and dust around you is not dense. By any terrestrial standard, it is an extraordinarily tenuous material, more vacuum than substance. But it is present. The instruments can measure it. The cameras can image it. And Rosetta, moving through this environment, must continuously update its orbital models to account for the non-gravitational forces that the outgassing exerts on its trajectory. The outgassing is not uniform. It is stronger from the sunward side of the nucleus. It is concentrated in the active regions where the surface composition and topography allow the most efficient sublimation. It varies with the comet's rotation, stronger when the most active regions face the sun, weaker when they rotate into shadow. The resulting pressure on Rosetta is not constant. The spacecraft pitches and rolls slightly as the outgassing environment changes around it. Its attitude control system, a set of reaction wheels and thrusters, continuously adjusts to maintain the correct orientation. The mission team on Earth has developed sophisticated models of the outgassing environment to predict these forces, but the comet is not perfectly predictable. Outbursts, sudden, short-lived increases in activity driven by subsurface pressure buildup and rapid sublimations can occur without warning. Rosetta has experienced several of these already. In each case, the spacecraft's autonomous systems responded correctly, adjusting orientation, protecting the science instruments, maintaining communication. But the environment is getting more intense. Perihelion is approaching. On August 13th, 2015, 67P will reach the closest point in its orbit to the Sun, 1.24 astronomical units, 1.24 times the distance from Earth to the Sun. Slightly farther from the Sun than Earth's orbit. From that distance, the solar flux, the energy per unit area arriving from the Sun, is approximately 65% of what Earth receives. That 65% falling on the dark absorbing surface of 67P will drive the highest activity levels the comet has experienced in this orbit. And you are here for all of it. The comet beneath you is about to wake up completely. The ice that has been preserved in the interior for 4.5 billion years is about to feel warmth it has never felt before. The jets are about to become geysers. The coma is about to become a storm. And somewhere on the surface of the large lobe, under a cliff in the region called Abydos, a small lander is lying in the dark, its circuits cold, its instruments silent. It has already done its work. It has already sent its data. It is already part of the story. And the comet carries it forward, carries it as it has carried everything on its surface, without preference, without intention, simply by being a body in motion in space, following the curve that gravity cut for it billions of years ago, toward the sun, toward the fire, toward the most dramatic few weeks in 67P's recent history. Rest now, if you can, in the calm before it. The comet is still moving. The orbit is still curving inward. And the sun, from here, is finally starting to look less like a star and more like a source of genuine warmth. Something is about to begin that has no equal in ordinary human experience. The waking of a comet at perihelion. You will be there, but not yet. For now, just move with the comet through this final quiet stretch, the last weeks before the closest approach, the last period of relative stillness before the surface erupts in the most spectacular sustained geological display occurring anywhere in the inner solar system on this particular August morning. The cold is still here, but it is losing, degree by degree, kilometer by kilometer. The sun is winning, and the comet knows it, not in the way that living things know things, but in the way that physics knows things, through cause and effect, through energy and response, through the iron logic of thermodynamics that has no exceptions and takes no prisoners. The ice must warm. The warm ice must sublime. The sublime must escape. And the comet, piece by piece, must give itself to the space around it. This is what it means to approach the sun. This is what 67P is about to do. Sleep now, if you can, before the storm. The universe will still be there when you wake. And so will the comet. August 13th, 2015. Perihelion. The word comes from the Greek, peri meaning near, and helios meaning sun. It is the moment in an elliptical orbit when the orbiting body is at its closest approach to the object it orbits. For 67P on this date, perihelion means a distance of 185 million kilometers from the sun. 185 million kilometers. To put that in context, the Earth is on average 150 million kilometers from the sun. 67P at perihelion is 35 million kilometers farther from the sun than Earth. It is roughly in the region of space between Earth's orbit and Mars's orbit. From this distance, the sun subtends an angle of about 19 arc minutes in the sky, slightly larger than the diameter of the sun as seen from Earth, because 67P at perihelion is closer to the sun than Earth's average position, though only barely. The solar constant, the energy per unit area per unit time arriving from the sun at this distance, is approximately 1,000 watts per square meter. Compare this to 67P's earlier position in the outer solar system, where the solar constant was less than 10 watts per square meter. The comet's surface at perihelion is receiving 100 times more energy from the sun than it was at aphelion. 100 times. The dark surface of 67P, absorbing 94% of that incoming radiation, responds. The surface temperature on the sunward side of the nucleus rises to approximately -10 degrees Celsius at perihelion. -10 degrees Celsius. This is the temperature of a moderately cold winter day in many parts of the world. It is a temperature at which liquid water could not exist. The atmospheric pressure above the comet's surface is far too low for liquid water to be stable. But it is a temperature that is more than 200 degrees Celsius warmer than the comet's equilibrium temperature in the outer solar system. And it is hot enough, more than hot enough, to drive vigorous sublimation of every volatile compound in the near-surface layers. You are standing on the surface of 67P at perihelion, or rather, you are crouching. Standing is still not quite right on this body because the gravity is still only 1/10,000th of Earth's. The perihelion passage changes nothing about the comet's mass or its gravitational field, but you are anchored to the surface in the way that the surface allows, your weight distributed across a wide contact area to avoid sinking through the low-density crust. What surrounds you is unlike anything you have encountered in this story so far. The surface is not still. It is moving. Not dramatically, not in any way that looks like motion at a human timescale. You will not see the surface flowing or shifting in real time, but at the scale of hours and days, the surface is in continuous transformation. Fine dust particles, dislodged from the surface by the expanding gas beneath them, drift upward into the tenuous space above the nucleus. Because the comet's gravity is so weak, These particles, once they have enough upward velocity to escape the uppermost layer of the surface, continue rising. Some of them achieve escape velocity and leave the comet entirely, joining the coma. Others fall back, landing gently somewhere else on the surface, redistributing material from active regions to less active ones. The coma around you at perihelion contains a density of particles that would be classified as a very hard vacuum by any terrestrial standard. There are approximately 1 million gas molecules per cubic centimeter in the densest part of the coma, close to the nucleus. On Earth's surface, there are approximately 27 million trillion molecules per cubic centimeter. But compared to the space between planets, which typically contains only a few molecules per cubic centimeter, the coma of 67P at perihelion is genuinely dense. It is, in the most technical sense of the word, an atmosphere. A temporary, asymmetric, constantly replenished atmosphere, driven not by the dynamics of a planet's gravity well retaining gas over geological time, but by the continuous sublimation of volatile ices from the nucleus surface, continuously lost to space, continuously replenished by the ongoing sublimation below. The water outgassing rate at perihelion is approximately 300 kilograms per second. 300 kilograms of water vapor leaving the nucleus every second. That is roughly the weight of a large car as water vapor evaporating from the surface of this small world every single second at peak activity. Over the course of 1 hour at perihelion, the comet loses more than 1 million kilograms of water. Over the perihelion passage, the few weeks centered on the closest approach, the total water loss is estimated at several 100 million kilograms. And water is not the only substance being lost. Carbon dioxide outgassing peaks at roughly 23 kilograms per second. Carbon monoxide, which has a sublimation temperature far lower than water or CO2, is outgassing continuously even in the moderate temperatures of the outer coma. Its contribution to the total volatile loss is significant, but harder to measure because it begins sublimating at much lower temperatures than water. Organic molecules, formaldehyde, methanol, hydrogen cyanide, acetaldehyde, glycolaldehyde, are present in the outgassing at various concentrations, each one released at a different rate depending on its sublimation temperature and its abundance in the near-surface composition. Rosetta at perihelion is not where it was during the quiet mapping phase of the mission. The spacecraft has retreated. The increasing activity of the nucleus, the growing density of the coma, the increasing frequency of outburst events, the greater momentum transferred to the spacecraft by the outgassing environment, forced the mission team to move Rosetta progressively farther from the nucleus as perihelion approached. By August 2015, Rosetta was operating at distances of several hundred kilometers from the nucleus. At 300 kilometers, the nucleus subtends only a very small angle. It is a relatively small object in the camera's field of view, but the coma is enormous. The imaging data at perihelion shows 67P, surrounded by a bright, diffuse envelope of scattered light, the sunlight bouncing off the dust particles in the coma, visible as a soft glow that extends far beyond the sharp edge of the nucleus itself. And the jets. At perihelion, Rosetta's cameras can image the jets directly. They are visible as discrete, brighter columns of material rising from the sunlit surface and expanding outward into the coma. The largest and most active jets can be traced for hundreds of kilometers before their density drops below the imaging threshold. There are dozens of identified jet source locations across the nucleus. The most active regions are on the sunward-facing parts of the large lobe's northern hemisphere, which, because of the comet's axial tilt, is the hemisphere receiving the most intense solar radiation during this perihelion. Each jet has its own character. Some are narrow and well collimated, tight columns of gas and dust that maintain their structure for long distances before diffusing. These tend to originate from confined sources, a pit, a crack, a region where the overlying crust is particularly thin and the gas pressure builds up to a focused release point. Others are broader and more diffuse, wide fans of material expanding from larger areas of active surface. These are driven by more distributed sublimation, large regions of the surface releasing gas simultaneously, the individual contributions merging into a collective outflow. On July 29, 2015, 2 weeks before perihelion, Rosetta's cameras captured something that the mission team had hoped to observe, but had not been certain they would see. An outburst. A sudden, intense, short-duration increase in the comet's activity, not the steady-state sublimation of the regular jets, but a violent, brief release of material from a single source on the nucleus. The outburst appeared in the imaging data as a bright plume emerging from the surface near the Atum region on the large lobe. Within minutes, the plume had expanded into a bright, diffuse cloud that temporarily dominated the local environment around the nucleus. The physical mechanism behind cometary outbursts is still debated. The leading hypotheses include the sudden exposure of a fresh volatile surface by a cliff collapse or mass wasting event, a slump of surface material that reveals pristine ice beneath, the buildup of subsurface gas pressure beneath an impermeable crust layer, which eventually ruptures, and the rapid sublimation of highly volatile clathrate ices, water ice structures that can trap other molecules inside their crystal lattices, releasing both the water and the trapped volatiles simultaneously when temperature thresholds are crossed. The Rosetta data suggests that multiple mechanisms are at work in different outbursts. The July 29th event showed characteristics consistent with a fresh surface exposure. The material in the outburst had a spectral signature indicating a higher fraction of ice than the usual surface material, suggesting that newly exposed material was driving the enhanced activity. There have been other outbursts. There will be more. In the weeks around perihelion, the comet experiences multiple outburst events per rotation, brief, intense periods of enhanced activity that temporarily alter the structure of the inner coma and send waves of denser material propagating outward through the gas and dust environment. You are in one of these events now. You have not been harmed by it. The material density, even at the peak of an outburst, is far too low to physically affect a person in any conventional sense. But you are surrounded by a suddenly brightened environment. The dust density around you increased by an order of magnitude for the next few minutes as the outburst material disperses. The particles around you are largely sub-micrometer in size, smaller than the wavelength of visible light in some cases, which is why the coma appears as a soft glow rather than a collection of individual visible particles. Some larger grains, up to a few hundred micrometers, are present as well. These are the particles that Rosetta's Giada dust impact detector has been directly measuring throughout the mission. GIATA, the grain impact analyzer and dust accumulator, detects individual dust particles as they strike its sensor surface. It measures the particles' mass, impact speed, and momentum. Over the course of the mission, GIATA detected thousands of individual dust impacts, building up a statistical picture of the size distribution, velocity distribution, and flux of cometary dust in 67P's environment at different distances from the nucleus and at different phases of the comet's orbit. At perihelion, the dust flux at Rosetta's distance of several hundred kilometers is thousands of times higher than it was during the early mapping phase. The comet is shedding itself in all directions. Looking outward from the nucleus, away from the sun, you can see the dust tail. You cannot see it the way a distant observer would see it, as a bright streak of light across the sky. From inside the coma, you are surrounded by the material that makes up the tail. The tail is not a thing you are outside looking at. It is a place you are inside. The dust tail forms because solar radiation pressure, the momentum of photons pushing on solid particles, acts differently on different sized particles. Very small particles are pushed rapidly away from the sun, forming the brightest, most distinct part of the dust tail visible from Earth. Larger particles, which have more mass relative to their surface area, are pushed more slowly. They lag behind the smaller particles, taking longer to be swept back by radiation pressure. They form a broader, more diffuse component of the tail. The result, viewed from a distance, is a curved dust tail, curving away from the direction of the comet's motion, because the most rapidly pushed particles are the smallest, and they are concentrated closer to the sun anti-sun direction, while the larger particles lag along the orbital path. The ion tail is different. Ionized molecules, water molecules, and other species that have had an electron stripped away by ultraviolet radiation from the sun are not just pushed by radiation pressure, they interact directly with the solar wind, the continuous stream of charged particles flowing outward from the sun at approximately 400 to 700 kilometers per second. The solar wind drags the ionized molecules directly away from the sun, not curved but straight. The ion tail is always directed anti-sunward, regardless of the comet's direction of motion. At perihelion, 67P has both tails well developed. Observers on Earth with telescopes can see the comet not as a spectacular naked-eye object, because the geometry of the orbits means 67P is not particularly close to Earth during this perihelion passage, but as a fuzzy object with discernible structure. Observers who have been following the mission, who know what is happening on and around the nucleus, are watching something extraordinary from their backyards. They are watching the physical process by which comets were understood, historically, mythologically, as signs, as portents, as extraordinary disruptions in the order of the sky. And now they are watching the same phenomenon with full knowledge of what is actually causing it. The iron logic of thermodynamics and orbital mechanics, and the interaction between a small, icy body and the electromagnetic radiation of a star. It is not less beautiful for being understood. If anything, it is more. Rosina, the mass spectrometer that has been one of Rosetta's primary scientific instruments throughout the mission, is working continuously throughout the perihelion period, sampling the chemical composition of the coma at Rosetta's orbital position. The data it is returning is reshaping understanding of cometary chemistry. The ratio of heavy water, deuterium oxide or HDO, in which one of the hydrogen atoms is replaced by its heavier isotope deuterium, to ordinary water in 67 Ps, outgassing is approximately 3 times higher than the ratio found in Earth's ocean water. This measurement has significant implications for the hypothesis that comets delivered Earth's water. If 67P is representative of the Jupiter family comets that bombarded the early Earth, and if 67P's water is too deuterium enriched to match Earth's water, then Jupiter family comets are not the primary source of Earth's water. The water on Earth may instead have come from carbonaceous chondrite asteroids, which have a D/H ratio much closer to Earth's ocean water, or from a combination of sources, some cometary, some asteroidal, in proportions that still need to be determined. This is not a failure of the mission. This is science working correctly, a measurement that rules out a hypothesis and constrains the solution space for one of the most fundamental questions in planetary science. Where does Earth's water come from? The data from Rosetta doesn't answer that question definitively, but it adds a constraint that any future answer must satisfy. In the final weeks of perihelion, Rosetta is doing something that the mission planners had never been certain would be possible. It is flying directly through the most active regions of the inner coma at altitudes of only 8 to 20 kilometers above the nucleus during so-called flyby observations designed to sample the near-nucleus environment at its most intense. These are high-risk operations. The dust density at 20 kilometers from the nucleus during perihelion is high enough that particle impacts on Rosetta's instruments are a genuine concern. The navigation uncertainty at such close ranges, with the comet's irregular gravity and the non-gravitational forces from outgassing both affecting the trajectory, requires continuous monitoring and frequent thruster corrections. The team accepts the risks. They did not send a spacecraft 10 years and 5 months across the solar system to turn back at the most scientifically interesting moment. During these close flybys, Rosetta detects a molecule that causes significant excitement in the astrochemistry community: glycine. Glycine is the simplest of the 20 amino acids used in the biochemistry of terrestrial life. It consists of a carbon atom bonded to a hydrogen atom, an amino group NH2, and a carboxyl group COOH. It forms spontaneously under a variety of non-biological conditions and has been detected in meteorites and in interstellar clouds. Its detection in the outgassing of 67P is confirmation that the building blocks of proteins, the molecular machinery of life, are present in the volatile inventory of a Jupiter family comet, not just preserved in the refractory, solid material of the nucleus, present in the gas that the comet actively releases into space. The Rosetta team takes great care in their analysis. Glycine is a small molecule with a relatively small mass, and distinguishing its signal from other molecules of similar mass requires careful treatment of the spectrometer data. The detection is confirmed through multiple independent analysis approaches. It is real. In the gas streaming off 67P at perihelion, there is glycine. There is methylamine. There is ethylamine. These are molecules that can participate in the formation of amino acids under abiotic, non-biological conditions. They are part of the chemical pathway by which the building blocks of life could, in principle, form in environments that have never contained life. And they are being released right now from the surface of this comet into the space around it mixed into the coma carried outward by the solar wind, distributed into the environment of the solar system. The comet is spreading its chemistry, slowly but continuously, over tens of thousands of orbits, over millions of years. The chemistry accumulates. You're here in the middle of it, standing on a surface that is 4.5 billion years old, breathing, in your imagination, in the metaphor that this experience allows, air that smells of nothing, because there is nothing here to stimulate an olfactory nerve, but that carries, in its molecular composition, something that the universe has been working on since before the Earth existed. The amino acid precursors, the sugar molecules, the phosphorus compounds, the alphabet of life written in the outgassing of a dirty snowball at perihelion. The comet does not know what it carries. The universe does not have intentions. These molecules are not directed anywhere. They are not aimed at anything. They spread in all directions equally, following the gradients of gas pressure and the vectors of radiation pressure and the flows of the solar wind, with no preference for planets over vacuum, for oceans over rock, for the conditions that produce life over the conditions that don't. But among the vast volume of space into which these molecules spread, there is, in this solar system, at least one small blue planet where the conditions are right, where liquid water is stable, where energy gradients exist, where mineral surfaces can concentrate organic molecules, where, given enough time and enough chemistry, something complex enough to metabolize, replicate, and evolve might arise. It already did arise. It arose before the evidence was assembled, before anyone could ask the question. And now, orbiting a comet at perihelion, carrying instruments sensitive enough to detect single molecules in a coma that extends for 100,000 kilometers, we are beginning to piece together what may have happened in the time before the evidence. The comet streams past. The tail extends for millions of kilometers behind it. The coma glows faintly with scattered sunlight. And on the sunlit face of the nucleus, the surface is being remade, slowly, continuously, by the same process that has been running for every perihelion this comet has ever experienced. Sublimation, loss, the giving away of substance. The comet is smaller than it was before this orbit began. It will be smaller still when the next orbit begins, and smaller again after that. This is the nature of comets. They are not permanent. They are passing through. Like everything in the inner solar system, they exist in the middle of a story, not at the beginning, not at the end, but somewhere in between, shaped by what came before and shaping, in small ways, what comes after. Perihelion has passed. The comet is now moving away from the sun. The rate of sublimation will decrease over the coming weeks and months, slowly at first, then more rapidly as the distance from the sun increases and the surface temperature drops back toward the levels that allow the volatile ices to restabilize. The jets will diminish. The coma will thin. The tails will shorten. The comet will become quieter. And Rosetta, the spacecraft that has been its companion for more than a year, orbiting, measuring, watching, will face a decision. A final decision? One that the mission team has known was coming since long before they arrived. Rosetta is running low on fuel. Its thrusters, which have been firing continuously for more than 12 years, for the gravity assists, for the main engine burns, for the constant orbital adjustments around the nucleus, have consumed most of the stored propellant. There is not enough fuel to do what the mission team would most want to do, which is to maintain the orbit indefinitely, to accompany the comet all the way back out to the cold dark of the outer solar system. There is only enough fuel for one more maneuver. The mission team has decided what that maneuver will be. Not a retirement into parking orbit. Not a shutdown in place, leaving the spacecraft to drift away from the nucleus and into a long, aimless solar orbit. Something more deliberate. Something that will put the spacecraft's instruments in the closest possible proximity to the nucleus for one final set of measurements. Something that will end the mission in the most scientifically productive way available. Rosetta is going to land on 67P. Intentionally? Slowly. In the same place, more or less, where Philae bounced 7 hours of descent into a different future than the one that had been planned. Rosetta will not bounce. Its descent will be controlled, its orientation maintained, its instruments active until the last possible moment. And then it will touch the surface, and the signal will go silent. And the story of the most ambitious comet mission in human history will reach its final chapter. That chapter is still ahead. But for now, the comet continues moving outward. The sun behind it. The outer solar system ahead. The cold returning, degree by degree, to the surface that was so briefly warm. Let yourself move with it. The speed is constant. The silence is returning. The light is fading slowly as the distance from the sun increases. The comet carries Rosetta with it, not because the spacecraft cannot leave, but because it has chosen not to. It has chosen to stay, to see this through, to the end. Rest now. The ending is close, and it is worth being awake for. But sleep if you need to. The comet will be there when you return. It always is. It always has been. It always will be for at least another 10,000 years before the sun finally takes the last of what it has. Rest. And let the comet carry you outward through the dark, back toward the cold, back toward the silence that was there at the beginning of this story and will be there long after its end. You are in good hands. The universe is a reliable host. It has been keeping this comet for 4.5 billion years. It can keep you for a few more hours. Sleep. The decision was not made quickly. It was made over months in meetings and in quiet conversations between mission scientists and engineers, in careful analysis of fuel margins and orbital projections, in the gradual acceptance of what the numbers were saying. The numbers said there is not enough fuel to continue. Rosetta had been launched with enough propellant to perform the gravity assist maneuvers, the main interplanetary cruise burns, the comet rendezvous deceleration, and more than 2 years of orbital operations around the nucleus. By the summer of 2016, almost all of it was gone. The remaining propellant, a few kilograms at most, was enough for small trajectory corrections and attitude control maneuvers. It was not enough to maintain a stable orbit indefinitely around the nucleus. The irregular gravity of 67P, combined with the non-gravitational forces from the comet's outgassing, reduced now but not zero, would eventually perturb any orbit beyond the ability of the remaining fuel to correct. Rosetta would drift away from the comet. That was one option. Let the spacecraft drift into a solar orbit, silent, its mission over, its instruments powered down, circling the sun indefinitely in an orbit not very different from 67P's own. The mission team considered this option and rejected it. Not because it was technically impossible, it was entirely possible, but because there was something better. The comet had moved far from perihelion by the summer of 2016. Its activity had diminished significantly. The outgassing rate had dropped by more than an order of magnitude from the perihelion peak. The coma had thinned. The jets had quieted to a fraction of their former intensity. This meant something important for orbital operations. It meant Rosetta could get close again. Very close. Closer than it had been able to get during the perihelion period, when the outgassing environment was too intense for safe close operations. Close enough to obtain imaging data at resolutions never achieved before. Close enough to sample the near-nucleus gas environment at altitudes of only a few kilometers. Close enough eventually to touch. The mission team designed what they called a controlled descent, a series of maneuvers that would lower Rosetta's altitude progressively, allow science operations at each stage, and ultimately guide the spacecraft to the surface at a speed low enough that the impact would be survivable for the instruments long enough to transmit final data. The target was the Mott region on the small lobe of 67P, the head. Mott is named after the ancient Egyptian goddess of truth, balance, and cosmic order. It is a region of moderate topographic complexity, with several active pits, roughly circular depressions from which jets have been observed, and a covering of fine-grained material that the mission scientists wanted to study at close range. The pits in Mott are particularly interesting. They are not impact craters. Their morphology, their shape, their depth to diameter ratio, their rim structure does not match what impact craters look like. They appear instead to be collapse structures, or possibly sites where subsurface volatile loss has removed material from below, causing the overlying surface to drop. Their walls are steep and their floors are covered in material that appears in Rosetta's imaging data to be composed of consolidated material exposing the internal structure of the comet, the same layering visible in the cliff faces elsewhere on the nucleus. These pits are in a sense windows. Windows into the interior of a comet. And Rosetta, in its final hours, would fly directly into one. Not literally. The controlled descent would bring Rosetta to the surface of Ma'at, possibly near one of the pits, possibly in the smooth material between them, but not into a pit itself, but close enough to image the interior of the pit walls at resolutions of centimeters per pixel. The kind of resolution that would take cometary science decades to achieve again, if ever. You are with Rosetta now. The date is September 29th, 2016. The spacecraft is in the final phase of its operational life. Its instruments are all powered on. Its transmitter is active, sending data back to Earth at the maximum rate the communication link allows. The distance from Earth to Rosetta at this moment is approximately 720 million kilometers. The signal travel time is approximately 40 minutes. This means that everything happening now on and around the spacecraft, every maneuver, Every instrument measurement, every camera image will be known on Earth 40 minutes after it occurs. Rosetta cannot be controlled in real time. The final descent is entirely autonomous. The mission team on Earth has uploaded the final command sequences, the precise sequence of thruster firings and instrument operations that will guide the spacecraft through its last hours. Those commands are stored in Rosetta's onboard computer, ready to execute at the precise time specified. At 0 hours Universal Time on September 30th, the final descent maneuver begins. Rosetta fires its thrusters. The firing is brief, a few seconds of controlled burn, but precisely calculated. It changes the spacecraft's velocity by a small fraction of a meter per second, just enough to begin a gradual, slow descent toward the surface. You are on Rosetta. You are falling. Again. But this time there is no 7-hour wait before the surface arrives. The final descent from the altitude at which the maneuver begins to the surface of 67P takes approximately 14 hours. And every one of those hours is filled with data. OSIRIS is imaging continuously. As Rosetta descends, the resolution of the images increases with every kilometer of altitude lost. Features that were tens of meters across in the orbital imaging are now resolvable to a few meters, then to a meter, then to less than a meter, revealing the fine structure of the surface in a level of detail that no previous image has shown. The Mott region below the descending spacecraft is covered in irregular patches of material, some smooth, some with a rough granular texture at this resolution. There are boulders, some of them several meters across, casting long shadows in the low-angle illumination. There are the pits, visible now as dark, roughly circular depressions in the surface, their interior walls showing the horizontal banding of the comet's internal layering. As Rosetta descends into the lowest altitudes, below a kilometer, below 500 meters, OSIRIS is returning images at resolutions of centimeters per pixel. Centimeters. Individual pebbles, individual grains almost. The finest texture of the cometary surface, resolved to a scale that no instrument has ever achieved from orbit around a small body. At this resolution, the surface of 67P is no longer dark and featureless. It is detailed. It is varied. It is a landscape. Not a landscape that resembles anything on Earth, not valleys shaped by water, not hills shaped by wind, not beaches shaped by waves. It is a landscape shaped by sublimation and collapse, by the thermal cycling of a surface that spends years in the deep cold and then months in moderate warmth, by the slow but persistent loss of volatile material from below, by the gentle redistribution of dust under the comet's feeble gravity. It is a landscape that has been here in roughly this form for millions of years, and it is being seen for the first and last time at this resolution by a machine that has been traveling toward this moment for 12.5 years. The Rosetta instrument is sampling the gas environment at these close altitudes. The composition of the outgassing at distances of only a few hundred meters from the surface is subtly different from what has been measured at greater distances. Some of the more reactive molecules, species that would normally be photodissociated or chemically altered before reaching the altitudes where Rosetta has previously operated, are detectable here in their original form. The data is being transmitted continuously. Each measurement, each image, each spectrum is sent back to Earth as soon as it is collected, because there is no certainty about when the data stream will end. At 11 hours 30 minutes Universal Time on September 30th, 2016, Rosetta is at an altitude of approximately 20 meters above the surface of Ma'at. 20 meters, the height of a 6-story building. The images being returned at this altitude show individual grains of cometary material, the constituent particles of the surface sediment, hundreds of micrometers across, casting shadows in the low-angle light. This is the surface of a comet. This is what it looks like from 20 meters. The last image transmitted by Rosetta, the final frame returned before impact, shows a surface texture of fine, granular material, relatively uniform in appearance, with a few brighter spots that may be small ice-rich patches exposed by recent surface activity. It is not a dramatic image. It does not look like the surface of an alien world. It looks like sand, or perhaps fine gravel, or the bottom of a very old, very cold, very dark river that has been dry for 4 billion years. At 11 hours 19 minutes, the signal from Rosetta stops. Not abruptly, the last data packet is transmitted and received on Earth at its expected time, and then there is no more. The spacecraft has touched the surface. The impact velocity was calculated at approximately 90 centimeters per second, somewhat less than a meter per second, significantly slower than a person walking at a moderate pace. At this velocity, on a surface with 67 P's material properties, the impact force is not enough to damage most of the instrument sensors immediately. There may have been a final fraction of a second during which the instruments were in contact with the surface, during which COSAC might have detected a final whiff of near-surface gas, during which the accelerometers registered the contact, during which MUPUS felt the temperature of the ground it finally reached. Those measurements, if they occurred, were transmitted and received. They are part of the archive. The European Space Agency declared the Rosetta mission complete at 11 hours 40 minutes Universal Time on September 30th, 2016. In the operations room in Darmstadt, the people who had spent years, in some cases decades, of their professional lives on this mission sat in silence for a moment after the signal stopped. Then they began to talk about what had been found, about what it meant, about what would be done next, because science does not end when a mission ends. It continues in the data. Rosetta returned more than 100,000 images of 67P's nucleus during its mission. It returned measurements of the comet's outgassing from dozens of instruments continuously over more than 2 years of close proximity operations. It mapped the surface to a resolution of better than 50 centimeters per pixel in the highest resolution images. It measured the internal structure of the nucleus using radio waves. It detected more than 500 distinct chemical species in the coma. It tracked the evolution of the comet's activity from more than 3 astronomical units from the Sun through perihelion and out to more than 3 astronomical units on the outbound leg. The scientific papers published from the Rosetta mission data number in the hundreds. The analysis is ongoing. Every year, new papers appear, new interpretations of the OSIRIS imaging data, new analyses of the Rosina mass spectrometry data, new models of the comet's internal structure based on the concert radio sounding results. The mission is over. The science is not. And somewhere in the data, somewhere in the enormous archive of measurements and images and spectra collected over 2 years of operations around a small dark body in the inner solar system, there may be answers to questions that have not yet been asked. The way it always works in science. You collect what you can, you analyze what you have, and the analysis opens new questions that couldn't have been formulated before the data existed. 67P is not done either. The comet is currently, as you listen to this in whatever year you are hearing it, somewhere in its orbit. It completes one orbit of the Sun every 6.45 years, so depending on when you are listening, it is somewhere between aphelion near Jupiter's orbit and perihelion near Earth's orbit, following the same ellipse it has been following since its orbit was first reshaped by Jupiter's gravity hundreds of thousands of years ago. Its next perihelion, after the Rosetta mission perihelion of 2015, occurred in November 2021. Its orbit has been refined by the Rosetta data to extraordinary precision. Scientists know where 67P is to within a few kilometers at any given time. They can predict its position years in advance with confidence. They can calculate exactly when it will next pass closest to Earth, and how bright it will appear in the sky, and from which regions of the world it will be visible. It is not lost. It is not gone. It is just farther away right now than it was at perihelion. On the surface of 67P, in the shadow of a cliff in the region called Abydos, on the large lobe of the nucleus, the Philae lander is still there. Its batteries are long dead, its circuits are cold, its instruments are silent. But the machine itself, the physical object, the metal and glass and polymer and silicon that was launched from Earth in 2004 and landed on a comet in 2014, is still there. It will be there for as long as 67P exists. It will travel with the comet on every orbit. It will approach the sun with it, experience the warming surface and the jet activity and the gradual loss of mass, and then recede with it back into the outer solar system. It will do this thousands of times. Unless the comet collides with something which is not expected, or is gravitationally ejected from the inner solar system by another close Jupiter encounter, which is also not expected on timescales of less than tens of thousands of years. Philae will ride on 67P until the comet is gone, until the last of the volatile ice has been sublimated, until the last jet has fired for the last time, until the nucleus, depleted of the gases that make it a comet rather than an inert asteroid, settles into a dark, inactive orbit and becomes simply another small body in the inner solar system. This will take tens of thousands of years at minimum. It may take longer. Some comets are more durable than others, depending on the depth of their volatile reservoirs and the rate at which those reserves are depleted by each perihelion passage. 67P's remaining lifetime as an active comet is uncertain, but it is long. Long by any human measure. Long enough that it is not worth worrying about. And in all that time, the comet will continue doing what it has always done, releasing material into the solar system, distributing the chemistry of the outer solar system into the inner solar system, leaving thin traces of itself in the orbital paths of planets. The Perseid meteor shower, which peaks around August 12th of every year and is visible from the northern hemisphere, comes from Comet Swift-Tuttle, a different comet with a different orbit. But the Draconid meteor shower, which peaks in early October, originates from the debris stream left behind by a comet called 21P Giacobini-Zinner, another Jupiter family comet, similar in many ways to 67P, leaving its material along its orbital path for Earth to pass through. 67P has its own debris stream. Earth does not currently cross it. But orbital mechanics are not static over geological time. The paths of planets and comets evolve. The resonances shift. And in some future configuration of the solar system, after the precession of Earth's orbit has moved its intersection point with the plane of 67P's orbit, Earth may cross the debris stream of 67P, and every year around some future date that no current calendar has a name for, the sky over the night side of the planet will light up with the descendants of the material that sublimated from this comet's surface during perihelion passes across the last few 100,000 years. Dust that was part of 67P. Dust that Rosetta flew through, that Giada counted, that Myro measured. Burning up in the upper atmosphere 80 kilometers above the surface of a planet that may or may not still be inhabited by anything capable of looking up and seeing it. This is the long arc of the story. This is what it looks like when you zoom all the way out. A comet formed 4.5 billion years ago from the same cloud of gas and dust that formed the sun and the planets and everything else in this solar system. Two pieces of that cloud finding each other, pressing together in the cold, becoming a single irregular body with a neck and two lobes and a surface darker than charcoal. Billions of years in the cold outer reaches, undisturbed except for the slow radiation of space and the gradual perturbation of gravitational influences, too distant to be felt as anything but a change in trajectory over millions of years. A Jupiter encounter, reshaping the orbit. A gradual inward migration. And then, in what is cosmically a very recent period, the comet begins passing through the inner solar system on a regular basis. Warming, activating, losing itself orbit by orbit to the sun. And then, even more recently, a fraction of a second in the timeline of the solar system, a species on the third planet decides to look carefully at one of these objects, builds an instrument, launches it, chases the comet across 12 years and 500 million kilometers, lands on it, listens to its chemistry, and discovers that the comet speaks in a language the planet recognizes. Glycine, amino acids, the molecules of life carried in the ice of an object that formed before life existed. Whether the comet put that language on the planet, or whether the planet invented the language independently and only later recognized it in the comet, that question is still open. It may be open for a long time, perhaps forever. But the discovery that the question is answerable in principle, that we can fly to a comet, land on it, taste its chemistry, that is new. That happened in our lifetimes. That happened in 2014 and 2015 and 2016 in missions rooms in Darmstadt and on a surface in the Abydos shadow and in the data streams that crossed 700 million kilometers of space to arrive at antennas on Earth. 67P continues its orbit, moving through space at 19 kilometers per second, following its ellipse, carrying Philae, carrying Rosetta's final resting place, the small depression in Ma'at, where the spacecraft settled into the surface at less than a meter per second on a September morning in 2016, carrying the organic molecules in its ice, carrying the record of the solar system's beginning in its undisturbed interior, carrying all of it without effort, because that is what bodies in motion do. They move. The universe provided the trajectory. Physics does the rest. You are here at the end of this story. You have traveled from the Kuiper Belt to perihelion and back. You have been present at the formation of a contact binary 4 billion years ago, and at the landing of a spacecraft 11 years ago, and at the final transmission of a mission that changed what we know about the building blocks of life. You have stood on a surface at minus 230 degrees Celsius and felt the warmth of a sun 150 million kilometers away finally reach you. You have watched ice become gas, and gas become tail, and tail become the material that drifts through the solar system and falls, eventually as the finest of particles, onto the surfaces of planets. You have been part of the comet story for the length of this night. Now let the story carry you the rest of the way. The sentences are getting shorter now. The science has been laid down. The comet is moving. The orbit is long. The solar system is quiet. Outside this moment, the stars are exactly where they were before this story began. 67P is out there, following its path. The data from Rosetta is sitting in archives in Darmstadt and in the computers of planetary scientists in a dozen countries, being analyzed right now at this hour by people who are still finding things in it, still asking new questions, still finding the story isn't done. But you can let it be done for tonight. You can let the comet carry you the rest of the way. Slow your breathing. Let the images settle. The dark surface, the fine grain of the Mott sediment, the long tails catching sunlight against the black, the chemical alphabet streaming off the nucleus, the small lander in the shadow of a cliff, cold and still, going wherever the comet goes. There is nothing more to do right now. There is nowhere else you need to be. The comet is out there. The orbit continues. The science goes on. And you are here very still in the long quiet that follows the end of a story that began before the Earth existed. If you have made it to this moment, thank you. Genuinely. This channel exists because people like you find something worth staying for in these stories, in the science, in the scale, in the particular kind of quiet that comes from thinking about things much larger and older than anything in ordinary life. If you have found something here tonight, a like and a subscription carry this work further than anything else can. The notification bell means the next story finds you. And there are more stories coming because the universe is not running short of things worth sitting with in the dark. Everything you heard tonight is real. The comet is out there right now. Good night.